visualization of your reaction sequence on your catalyst. So even then, it will be useful. Also, it will be useful in looking at how reactive different surfaces to the reaction. So you have different phases of your crystal. Let's say because your catalyst is the picture you have. The catalyst is a little powder, and the powder has different phases on it, and different phases have different reactivity. So with ultra-high vacuum, you can at least study which kind of phase you want to optimize in the design of your catalyst. So in that sense, it's useful to probe fundamental information, but in terms of, certainly in terms of catalyst, in terms of doing particle kinetic modeling, you do need the real pressure in order to simulate the reaction rate and things like this. So it's useful from the fundamental point of view, and certainly in terms of nanosciences now, the pressure gap problem is no longer an issue because a lot of the stuff is created in vacuum. So certainly chemical vapor deposition, physical vapor deposition to create nanostructure is all done in vacuum anyway. So you already create this sort of material in vacuum. All the thin film that you make in semiconductor industry is done in vacuum. In fact, in ultra-high vacuum for building Pentium chips and the new generation of CPU is all done in ultra-high vacuum. So for those problems, it's not an issue. But for chemistry, it is true that there could be an issue, especially when you're dealing with catalysts. The other issue is that when you are talking about surface science, you want to characterize your surface. So and you really don't want very dirty surface because then you are studying dirt, right? But and there's another criticism about surface science is that you're not studying real surfaces because you created clean surfaces, artificial clean surfaces, and then how do you connect to these dirty surfaces that in real life, right? Because most of the time you have dirty surface, and this is a problem. I mean, this is really a problem. But the proponent of surface science would say that you can put dirt on your clean surface and study the effect of dirt on your clean surface, and people have done that. Ideally, in real life, if you create your nanoparticle, for example, in a solution, then it will be covered with carbon or oxide, right? So then people would say, let's clean off this carbon and oxide, and then you put artificially control amount of carbon and oxide on your nanoparticle, and then you can study the effect, overall effect of this dirt on your surface. And it has been found, in some cases, your carbon, in fact, your dirt is very useful. Your dirt, in fact, is the one that promotes the reaction, could act as catalyst. So this, the amount of dirt on your surface could be an important component of your nano object. Okay? But it is part of the game because in order to analyze, you certainly have to break it down into pieces, start with clean, and then put dirt on and see the effect of the dirt on your overall nano object. And so in that case, you still need surface science to analyze these. Okay, so these are the sort of couple of common problems that people may brought up in terms of surface science, but I would say you still need that to know about, you need the surface science technique to probe a real particle, probably with dirt on it, to see what you got.
What is the thickness of surface that we are talking about here?
I'm sorry?
What is the thickness of surface that we are talking about?
Okay, so the question is, what is the thickness of the surface that we are talking about? We haven't defined the thickness of the surface yet. We will define that very shortly. So at the moment, you can think of a surface is an imaginary plane of two-dimensional grid, right, with particle on it. Think of it that way. So think of a three-dimensional crystal, and then you look at the top layer of your crystal as your surface. But really, as we go on, we will define this in a more precise way. A surface in that case will be several layers until you hit the layer that
same property.
that the physical structure of that layer doesn't change anymore. So usually it's 2 or 3 layer, monolayer. But here, when we're talking about analytical technique, we are talking about the front end, the top layer that your particle beam see, and that will be the first surface. So in that sense, so that's a good question that people should be aware of what people mean when they talk about surface, and people would mean different things as they switch from one jargon to another. All right. Back to I want to give you a quick tour of these nano-analytical techniques to look at surfaces, and we'll come back to this perhaps in more detail later on as we talk about individual topics for electronic structure and physical structure and things like this. But for now, I just want to give you a brief overview of what you will see. And some of these you have heard about, some may not, but I like to just give you a quick tour for now. Okay, so quick tour of survey analysis technique. And there are many ways to examine the surface property, and each involve a different setup and different physics of using this technique. And none of these are perfect, and you need to combine many of these methods together in order to get the complete picture of the surface. Okay, so and there are many listings. So here's one of the listings that I use. It's by no means an exhaustive listing. This is one of the listings. There are many similar type, but I'll just cover the main bit, the most common one that surface chemists use. That if you step into a lab with a lot of stainless steel chamber, you can recognize some of these tools that surface chemists use to probe the surface. Okay, and again, these are generally classified into 3 types of information, as we discussed. Structure here means physical structure of the surface, and then of course you have electronic structure, and then you have composition of the surface. So usually it's classified very much like what we are planning to do: physical structure, electronic structure, and composition. And then of course composition you need, because that leads to chemistry, that leads to processes, right, that you can do once you know the composition, chemically makeup of your component. And I don't want to go into these now, right, because I just want to you see in surface science there's a lot of acronyms, and this defines some of the acronyms that you will see. And as we get to it, you get a little bit more familiarized with some of these acronyms. But the point is that you need to send in some sort of particle beam, in either a photon beam, or electron beam, or an ion beam, right, or a molecular beam, right, neutral molecular beam, into your material to get something out, to probe. That will be your probe beam to interact with the surface and then see what happens to get this information. Okay, so generally that's what it is. It requires some sort of probing. Or of course, there's also temperature. You can also heat this material up to see what happens. Okay, and we'll run through these. So these are numerous techniques. If some of you recognize them, that's great. But if not, don't worry too much about it, because we will go through at least the key method of analyzing some of this stuff, and they are useful from these 3 different class of information that we have seen. There's some more discussion in Summerjai's book, but I like to go to the Charles Evans website. Charles Evans website is Evans website is Evans is a company that well-recognized company that do surface analysis for people. They do contract work, essentially. You can send them sample, and they run various analysis for you. And they have a nice website.